Well, it's the weekend and you know what that means. Time to implement ray tracing in one weekend using ray tracing in one weekend. Well, I mean, I don't know you. It might be a Tuesday for you. This is a YouTube video after all. This book is the first book in a 3-part series, and it's written in C++, so my goal is to do some ad hoc conversion and get a result in Rust, then in a future video, maybe convert that to WGPU. So anyway, what is ray tracing and what are we actually going to be doing? Ray tracing itself is a term that has become more ambiguous over time as more techniques were developed. We're using it here to mean the idea that you can render a scene similar to the way in which a camera does, in which real-world light is everywhere and the camera collects whatever portion of that light hits the sensor. In our ray tracing exploration, we'll be shooting rays out from the camera, since we don't really care about light that doesn't hit the sensor, into a scene. Those rays will hit something, bounce around hitting other objects, and we'll take a bit of color from each of those collisions to determine what color should show up at a given pixel. This can also be called path tracing because we're following a ray as it bounces around, and the full sequence of all of those individual rays is called a path. The objects in the scene will be mathematically constructed. So instead of having vertices and meshes, we'll have the here's an equation for the space a sphere takes up when it's centered at point 0,0 in the scene. On to section 1 then, PPM files. Now, PPM is an image format I've never heard of before this, but it's the one that this series uses, so let's get into dealing with it. The format itself is pretty straightforward, but the description in the series didn't quite connect with me. If we look at the PPM example screenshot here, this first line declares the range of numbers in use, which the article describes as being in ASCII. And if we go to the Wikipedia page, we can see that this is just a screenshot of what shows up on Wikipedia. There is a little bit more explanation for what the format looks like on Wikipedia if you're interested in reading it. The first line declares the range of numbers in use, which the article on Wikipedia describes as being in ASCII. What this means is we'll be using a U8 to represent the R, G, and B values just like CSS. So we get a number from 0 to 255, as you see below. Each of these represents a single color for either the R, G, or B channel. Then we declare how many pixels there are. First the number of columns, then the number of rows, so 3 columns, 2 rows, as you can see on the right-hand side here, followed by the max value, which is for us 255. So ideally we'd create this, 3 by 2 pixel image first, but the code that the article shows is not for that image. You'll also likely need additional software to display these PPM images. I chose to add a VS Code extension to use them, although viewing a 3 by 2 pixel image is kind of tough and I had to zoom in to 6400%. But so far so good. I grabbed iter tools for the Cartesian product function, which is very nice when iterating over all the pixels in a grid, and something I use in Advent of Code every year. For us, Cartesian product is a fancy math name for getting the XY coordinates of every point, where the width and the height are defined by ranges. This means we don't have to deal with the nested for loops, or worry about any indices. The screenshot in the article doesn't make it clear that you don't actually need to chunk these on like a 3 by 2 layout in the file. So if you look at the actual output that I've generated here, it does do this chunking of putting 3 pixels on each line. I later figured out that this isn't something you needed to do, but I am using chunks here in this initial code. Then finally, it's a matter of just writing that out using a format macro. This issue of the series showing me something that then doesn't actually need to be done is a common theme throughout the series. So in the first example where it shows this 3 by 2 grid of pixels, and then we don't actually need to do that, is a forward and back movement when reading this article that will happen over and over again. After cleaning up the code a little bit, when we realized that we didn't need to do that, we've then written out all of the pixel positions as colors. With the PPM file being written out and being able to be viewed by us, the series wants us to immediately implement a progress bar. This is the first deviation from what the series does for us due to the fact that we are using Rust and not C. As soon as I saw we needed a progress indicator, I reached for Indicatif. This crate provides a progress count function that we can just append to our iterator that we've generated here, and it will output a progress bar. Unfortunately, at this point, the progress moves so fast that it's only a single frame of a video, but that will change later when our program runs for a longer period of time. Next is creating a whole Vec3 interface, and I plan on having a pretty heavy WGPU bevy style angle to this work as I progress with more advanced implementations, so I'm going to go grab the Glam crate instead, which provides dvec3, a 3-dimensional vector that uses f64 as the type for the x, y, and z components. Glam does have a number of different types for all sorts of different vec3s, vec2s, vec4s, matrices, and so on. But honestly, I don't feel like I have enough context yet from the series to make anything AVEC3 though, so we're not using it in our program yet. So with that, I haven't made any adjustments to the program other than bringing in the dvec3 from Glam at the top of the file so that we can use it later. One part of this series that I found repeatedly awkward, like I mentioned a little bit earlier, is that a lot of the code is given before being shown or being told how it's going to be used. So we have to build a ray class here to represent a ray from some origin angled in some direction. This is effectively just storing 2 points in 3D space. The class itself is fairly straightforward, although since I don't really know how this code is going to be used, I chose to make a simple translation to a struct with an associated function called at. This allows us to take the origin point and find a position from that point in some direction at some distance. The at returns a 0.3, but I'm using a dvec3 for everything right now because I don't want to over abstract my Rust code and prevent myself from being able to extend it later when we get to a different part of the tutorial. So that means that this dvec3 is representing my colors, my points, and anything that is effectively XYZ. We're supposed to send rays into the scene now, but first we do a bunch of little math to generate a viewport. The coordinate system we're going to be using for this viewport in the scene matches Bevi's, so intuition about where objects are should translate well for us. You can see a whole bunch of different ways to handle this that Freya has put together. Bevi, of course, was added by IS, who maintains the Bevi cheatbook. This section is a lot of little fiddly math conversion and some constants, but it's nothing really that interesting. If we consider the image we're generating to have a grid of pixels, then our 0, 0 pixel is in the top left. And we're also storing the distance between pixels so that we can calculate where a given pixel is on the screen later. Overall, for every given pixel in the screen, we get that pixel center, we build a ray, and we send that ray into the scene. The origin of the ray here is at our camera's center, and the direction the ray is going in is the pixel location. The code here for generating color is fairly arbitrary. All of these numbers are building a gradient from this blue to white, but this color function is basically supposed to be giving us back the color that this ray is hitting. If you're clever or read the post very closely, you'll figure out that this is a lerp. And yes, Glam and dvec3s actually include a lerp function that we could have used here. This is just another example of the series manually implementing something that we just have functions for. With the camera set up, we can move on to rendering a sphere. Our sphere ends up looking like this, which doesn't really look like a sphere, but I promise you it's a 3D sphere. Rendering a sphere is the meat and potatoes of ray tracing, or so you'd think, I guess. At this point, we're successfully shooting rays into the scene and rendering the colors of the positions they hit. So to render a sphere, we need to use the equation of a sphere. That'll define where a sphere would be, and then we need to figure out if our ray would hit a place that sphere would be. This process reminds me a lot of signed distance fields, which Inigo has a lot of documentation on. Instead of using SDFs though, we're using intersections. If we were using SDFs, we'd have to use a slightly different approach called ray marching instead of calculating these intersections directly. And if you read the code on screen or click the link in the description, you'll see that the intersection code here is very, very, very similar to the intersection code that we have to write in hit sphere. In our color function, we call the hit sphere. If it hit the sphere, then we return the color red. And if not, we return the background, which gives us our red circle with the background. Like I said in the beginning, this doesn't look much like a sphere. It looks like a flat 2D circle, but that's only because we haven't shaded the sphere yet. We're about to do that in the next section though, using the surface normal vectors. Every point on a sphere has a normal, which is a vector that points exactly outward from the center of the sphere through the point on the surface of the sphere that we're looking at. Using these vectors, normalized so they have a length of 1, gives us colors we can paint onto the sphere. If you're not already familiar, a normalized vector means that that vector has a length of 1, which means all of the components are going to be less than 1. And if we use that directly as a color, we have an R, a G, a B component from 0 to 1 for each of them. If we directly use these vectors, the R, G, and B components corresponding to those normal vectors paint directly onto the sphere as different colors. We just need to multiply that by 255 to get the color. This section was a bit in the weeds and includes a discussion of square root and why you shouldn't try to remove it. But some of the discussion isn't as relevant because we're using Glam's dvec3. This dvec3 already has normalized functions and other utilities for us. Basically, I consider this another win for using Rust and the foundational crates in the ecosystem to power our ray tracer. We don't have to implement this normalize function. Either way, this hit sphere function is about to get a refactor. Ta-da! Our hit sphere was refactored. I felt a bit surprised by this section because it says that it's simplifying the ray sphere intersection code, but it doesn't feel like the code got any simpler. It's the same number of lines and still uses the dot function and other small fiddly bits of math, so I guess they mean mathematically simpler, but it doesn't really come through in the resulting code, in my opinion. The single letter variable names here were also not helping me very much, even though I'm already familiar with the quadratic equation, which is what we're using here. In any case, nothing changes visually here, and it's not like we have benchmarks, so it's hard to determine what the changes here are actually for. However, we immediately roll into creating an abstraction for hittable objects. The next few sections are all very C++ specific. There's an extended discussion about creating an abstract hittable class, followed by introducing C++ language features. There's also a number of constants we don't need to define, like pi, because we're using Rust. And Rust already has a pi constant in the standard library, as well as the infinity, even though we're not even using these yet. There's also a class definition for what is basically Rust's range type that we don't need to write. Overall, these sections are all dedicated to adding a second sphere. But it definitely took a while to get through and parse out what was actually necessary, given that Rust seems to provide a lot more for us than C++ does. Overall, the big point here is that I chose to implement hittable as a trait. I'm not sure this was the most straightforward choice, since later on we end up with an enum that encapsulates a lot of the same objects that also implement hittable. But it was definitely the choice that seemed to align most with the C++ code at the time, and I wanted to make sure that I was able to finish the series rather than spending a bunch of time refactoring. The hittable trait implements this hit function. This hit function takes a ray, which has an origin and a direction, and an interval to check, which is just a range. One of the other big changes here is that while the hit function for the abstract class inside of the series takes a hit record as a mutable argument and then tries to modify that inside of the function, but then also just returns a Boolean from the function, I chose to return an option type here. This is partially because the C++ code doesn't actually need to pass in a mutable object here. It just instantiates what is effectively an empty hit record, passes that into this function to mutate, and then uses it later. So in our case, if we don't have a hit, we don't need to create that hit record, and we return none. But if we do have a hit, then we do return that hit record. That lets us use iflet to check to see if we actually have a hit whenever we use this hit trait function. If we do, then we do something and we color it, and if we don't, we return that background color that we tried to create earlier. We also create a struct called hittable list here, although if you notice, this is not quite necessary to create, and we don't actually have any functions on this hittable list that aren't already functions on a vec. So in the C++ code, they create this hittable list, and they define this add function, but add is only pushing objects into a vec, so it's a very weird abstraction. We already have a clear function on vecs in Rust, and we already have a push function on vecs in Rust. So this abstraction for hittable list turns out to be not necessary, and I do end up refactoring this later to implement hittable for a vec. After implementing the hittable trait and building up a hittable list for a list of hittable items, we move into creating a camera class and doing some more abstraction. This is a pretty common theme inside of the series, doing a little bit of code and then refactoring or abstracting into, more abstract code. At this point, we're getting to a couple hundred lines of code, and I wanted to mention that I did put everything for this first run through, so there are no extra files, there are no extra imports. Everything's sitting in this one file. The series wants us to take the color function from the ray and put it on the camera class. But to be honest, that didn't make much sense to me because it doesn't use anything on the camera class to do the work it needs to do. So I left the color function on the ray struct instead. Small spoilers for book 2 in the series, there is actually a background color that could be a reason to keep the color function in the camera class, but it's easily handled the way that we have it here as well. The ray color function already has to accept the entire world of hittable objects, so we're not really losing anything by leaving this function on the ray instead of putting it in the camera class. Otherwise, we've taken a lot of the constants that we had at the top of the file and we moved them into this camera struct and built this initialization function called new that does all of the same logic that we had before. We also have this new render to disk function that handles all of the same stuff that we were doing before and writing out the ppm file. Next comes the problem of pixels and what pixels actually are for us. The issue a pixel is not a little square that's linked to in this section seems like one of those fallacies of distributed computing or falsehoods programmers believe about time, names, etc. type documents. Basically, it's a document that says, hey, you think of this simple thing in normal life, but it's actually horrendously complicated and not at all that straightforward. If you read through this article, you may come to the same conclusion as me, where in my mind, the big lesson for this section is that pixels don't really exist. They're actually a representation of a bunch of samples that we take and then represent as a pixel. And this idea of sampling a bunch of times inside of one pixel's space and then merging those samples is what allows us to power functionality like anti-aliasing as well as other materials. We get to ignore a section here about C++ not having random numbers in some versions, similar to the way that we get to ignore C++ not having ranges and other functionality. When we need random numbers, we're going to use the rand crate. This actually provided a great opportunity to use something that I don't really get to use very often, but is actually a fantastic function, the sum function on iterators. This is a really fun function because in its simplest case, it would be used for adding, say, numbers or something like that, but it can actually add anything that can add together. So in this case, we can add together dvec3s, which means that if we get the color from the ray and we multiply that by 255 to make it a number from 0 to 255, we can multiply by some scale factor. So we've got some number of samples that we're getting from each pixel in the image. If, say, we have 10 samples for one pixel, then for every color that we get, for every ray we send through that pixel, we need to multiply that by 1/10 so that each sample makes up 1/10 of that final color. With 10 color values, then, that are each 1/10 of a color, we need to sum all of those together to get the final color. And we don't have to use any functions like fold or reduce or whatever to do this because we can just take advantage of the fact that dvec3s can already add together and we can call the sum function. We've now added some randomness to the directions of rays that get sent through each pixel, that is our samples. By accumulating the randomized samples like we were just talking about, we get smoother edges on our circles rather than the very hard jagged edges that we had before. And this is anti-aliasing. With the ability to sample more data from each pixel, we can start building more complicated materials. It's also worth noting at this point that if we cargo run right now without release enabled, we do get quite a slow operation. It's not terrible, you can see it actually finishing as I'm talking right now, but if I cancel that and I run with release mode, you can see just how much faster this actually goes. It's done before I even finished my sentence. So it's a reminder to use the release flag when you care about performance, but also a moment to be thankful that we did add that progress bar at the beginning. Handling diffuse materials requires some randomness in scattering rays when they hit a surface, as well as the ability to combine multiple light ray bounces after scattering the rays. As you can see in this image, the rays come out of our camera, hit some sphere with some material on it, and then bounce around, maybe bouncing off into a random direction or bouncing off the other sphere once or bouncing back and forth and going up. Since we're using recursion to do this, we need to limit the depth of that recursion. And as I went through this, I was definitely hitting stack overflows before the series told me that we were actually going to limit the depth. Another problem of an answer being later in the series than the problem. I had to skip ahead twice during this section to fix a program that was either broken due to a stack overflow or producing what seemed like incorrect output. In my case, the sphere colors seemed way too dark to even be detectable as color. And that's because this difference between 0 and 0.001 mattered a lot more for me than it seemed like it mattered in the post itself. All in all, the sphere starts looking very cool at this point, if, a bit noisy. This whole section is about creating that diffuse material with the Lambertian, I'm not sure, distribution, which is basically when a ray hits the sphere, we want more of the rays to follow along more of the normal path than being completely random in any direction. The lesson for this section is don't be afraid to read ahead in this series because the answers are often not in the section that you're actually reading, and might be 3 subsections ahead. The change to use the Lambertian reflection is a really simple change. I say simple because it was really only one line, compared to the now 400 that we've written. Before this one line change, any rays that hit a sphere were scattered completely randomly, as shown in this image. But now, since we're using the Lambertian distribution, that's kind of just a fancy way to say the rays bounce off closer to the normal direction more of the time. Remember, the normal direction is the vector from the center of the sphere through the point that we're hitting and straight out. This results in stronger shadows and reflection from the sky. Also interesting from this section is we've got a couple of utility functions like random in unit sphere and random unit vector that we get to use normalized for. And instead of using for loops, I'm using the loop construct inside of Rust with that rand gen range to get a range from -1 to 1 for each component in the DVEC3. Image viewing programs assume that an image has been gamma corrected before being saved. Currently, our image colors are in what's called linear space, which tends to mean evenly distributed from 0 to, say, 255. But we want it to be in a gamma space when we save it, because most viewing programs on our computer are going to assume that we've done that. The gamma correction change went just as quickly as the reflection change that we just did, effectively being just a single line or two. The entire linear to gamma transformation is just running a square root on whatever value that we have for R, G, or B, and we apply that to each of the components in our vec. Then we've got our gamut change before as well as after. On to more materials then, in this case, metal. The metal section spends a lot of time describing material abstractions before describing how they're actually going to be used. There's an abstract class here to help define materials, but since I control everything here, I made material an enum, which you can see here on the right. We won't be extending this type outside of the confines of this program anyway, so having an enum that we fully control is exactly the kind of complexity that we need. We don't need to make this a material trait and deal with the additional complexity of having done that. I find myself flipping back and forth a lot because of things like functions that take arguments that are then mutated, but then also return Boolean values, which is a pattern that we see quite a few times. The pattern of creating empty variables and then filling them mutably instead of returning them feels very strange to me. We have the ability to return option types in Rust and use patterns like if-let, so I chose to return hit records instead of mutating them overall. The series also defines some utility functions that, again, already exist in Glam. For example, this near zero function is the absdiff-eq function with a vec of zeros. This is also the first time I ran into any issues with borrowing moved data, the first time I needed to derive clone on anything. Partially because the C++ code is trying to kind of circularly reference itself at this location in the series. We've got the sphere, which has the material and owns that data. And then we've got the hit record, which also owns the material. And then we've got the material itself. So I might have been able to actually refactor this into something else. But again, I don't know where we're going in the series at this point while I was going through it for the first time. So I chose to do something that was more amenable to being extended later. And I derived clone in 2 places and just kept going forward. There's also a component of the metal materials that determine how kind of fuzzy the reflections are. But while I was writing this, I realized I had an issue with how dark my images were. Turns out that due to the flipping back and forth that I was doing during this whole series, I had forgotten to go back to a small clamping function. This was back in the gamut section. Luckily, clamp is a widely implemented function in Rustland, both on regular F64s and also on DVEC3s. So I used that and just moved on to the dielectrics or glass materials rather than implementing clamp myself. In the dielectric section or the glass material section, they say the hardest part to debug is the refracted ray. But honestly, we haven't debugged much of anything yet. And there's largely been no discussion of debugging so far. That said, adding the new glass material is pretty straightforward, since adding a new material is now equivalent to just adding a new enum variant, and then in the scatter function on material, defining how that scatter should happen. So we add the glass material in the same way we've constructed the previous 2 materials, and we move on. We also want to start setting up more scenes, so moving the camera around and configuring it is what we get to next. In the positionable camera section, they say cameras like dielectrics are a pain to debug. but it was pretty tough for me, or at least I found it extremely awkward to switch the scene and the camera variable settings at the same time. For some reason, I had made a mistake that caused no balls to appear in the scene, but I didn't know if this was because the balls themselves weren't rendering or because the camera was pointed in the wrong direction. So I wish we had either used the same camera settings throughout this section, or at least had an indication that we were going to move back to the same scene. I will say that pointing the camera in certain directions greatly influences the render time of a scene, and this makes sense because if your rays are bouncing around for all of your samples, they will take more time, whereas if they just kind of miss everything, it doesn't take very long at all. The math in this scene is also spread across a growing camera initialization section, which makes it harder to go back and check against. And once you're kind of in this implementation phase, it's hard to go back and use the original camera to see where you came from and where you're going. It's also very unclear to me why we default to certain settings and then immediately change them without checking the result here. Overall, this also feels like what tends to make ray tracing harder to get into. There's kind of a complete lack of support and context when something goes wrong, which we see have an impact in the next section. The next section is the one that has us implement depth of field, or defocus blur is what we're calling it in this series. So we implement focus distance as well as defocus angle. I ran into an issue implementing this, though, that was pretty hard to debug. My focus distance didn't seem to be affecting the scene at all. The image has the blur applied uniformly across the entire image, no matter what I tried. So the image is either perfectly in focus or very blurry, and there's no real depth of field effect. I ended up just not fixing it because we're kind of at the end of the book anyway, and planning to come back to it later. Although, to be honest, I haven't come back to it between my implementation and the making of this video. I'll probably try to come back to it when I do the next implementation instead. That was the second to last section though, so we are right at the end of book 1, which has us build quite a large scene. And at the end of book 1, I was thankful for the progress bar we inserted at the beginning. Performance hasn't been something I've been focusing on very much, preferring instead to focus on the extendability of the program so that I can continue following the series. So when I set up the final scene and ran the program to render it, I immediately realized it was going to take a while. The final image was about halfway done by the time I had completed the Rayon refactor. Adding Rayon is usually super easy, but because I chose to make Hittable a trait and store hittables as trait objects, as we can see here with Dyn Hittable and box inside of Hittable list, I had to extend the requirements placed on the objects I was storing to also be sync. Now, sync and send are two traits that sort of go hand in hand and are more marker traits than anything else. You don't really implement sync. The Rust compiler tells you whether your type is sync or not. This is because Rayon is a work-stealing data parallelism approach that distributes work to available threads, and thus references to our data have to be safe to send across threads. This sped up the final image render to just about 4 minutes, or just under 4 minutes, whereas the previous render was, I think, going to take half an hour. It was about 15 minutes in when I stopped it. Adding Rayon is one of those things that I feel really shows off Rust's ability as a language. Instead of .iter, we use .into_par_iter, and we're off to the races, quite literally. I chose to put our parallelization on each pixel, and I didn't worry too much about testing other alternatives because the performance improvement that I got from putting the parallelization on each pixel brought the runtime down to an acceptable amount. After finishing book 1, I continued to refactor my code and clean some of it up. I'm fairly happy with the refactor in terms of organization, but I wasn't able to translate as much of the series to things like introducing alternative shapes as I would have liked. I broke out all of the examples that we were running into a new examples folder. So we no longer have a main.rs. Our lib.rs is just re-exporting, or exporting in the first place, our camera, the hittable interface, our materials, the ray struct we covered, as well as some shapes. The sphere shape and its hittable implementation live in one file, and then I've got a couple of attempts at different other shapes like a box, a cylinder, a rounded box. Each needs a bit more debugging work before it actually works, but that's okay. I do wish there was a bit more explanation for implementing these kinds of things on the internet. And if you've ever done any work in the space, you might be already familiar with the best resource I found, which is Inigo's site. This is something I showed off earlier in the video, which had our sphere intersection code, but it also has boxes, rounded boxes, hexagonal prisms, wedges, capsules, and a whole bunch of other different kinds of shapes. Unfortunately, on this page, there's not much explanation. There's a link to a shader toy example that you can run that often has a couple of comments in it, but there's a lot of single, double, and triple letter variables, as well as not really that much explanation. Probably the biggest change in this refactor is that I implemented this shapes enum rather than going with the vec of trait objects that we were doing before. Shapes now encapsulates each of the different hittable objects, and hittable is implemented for vect in this case. I do change this up a little bit later and implement it for, I think, slices if I remember correctly, but we no longer need to store trait objects, which makes working with everything in the examples just a little bit easier. I also decided to implement a camera builder API. You can see the impact of that here. So anytime we want to actually configure something on our camera, we can now run initialize and then call any of the functions that we want and leave the defaults for later. Finally, we run build and the camera actually does all of the calculations with the values we've given it, which is all of the code that we had before that was setting up the viewport and the pixel distances and so on. And that's all great because I actually did finish all this work in one weekend. So it was actually ray tracing in one weekend. That said, there is ray tracing the next week that I also started to get into. All right, so I've messed around enough with the path tracer we built last weekend, and I feel like I'm ready to move on to the next installment in the ray tracing series, ray tracing the next week. This one covers a whole bunch: motion blur, bounding volume hierarchies and axis aligned bounding boxes, texture mapping, Perlin noise, and more. It even looks like we get to make some quadrilaterals, so maybe I can debug my broken box implementation. Overall, the series claims that you can do these sections in any order, but from a light skim, that's only kind of true, so I decided to go through them in order. The first section, then, is motion blur. This introduces some concept of time, which we now need to store in each ray, because what we're doing here is effectively launching rays at different points in time, which then determines where an object is and whether or not the ray will actually hit that object at that time. This seems to be a very static concept of time. Since this isn't a real-time ray tracer, I suppose that makes sense though. We then need to extend our sphere struct. The C++ code just adds more fields to the class that may or may not be set, including a second center as well as an isMoving flag. Having both a second center as well as an isMoving flag feels kind of strange. If we have a second center, surely we're moving by definition. I chose to mostly follow the C++ code's model and refactor later if it makes sense. In this case, the sphere new function takes the basic fields that you would need to create a sphere either way, and then adds an additional with move to function that allows you to set a second center and does the calculation to store the value that we actually need in the sphere. This gives us a sphere new with our three values and then a with move to function with our new position. So motion blur check. On to efficiency structures. So we don't really have a speed problem in our ray tracer per se. The scenes we're working with are rendering fine, and while they could be much faster, writing a ray tracer in a CPU-driven language like Rust, instead of working with a GPU, is always going to slow us down. Personally, I don't feel like I'm writing this to be fast. I'm writing this to play with some light ray tracing and to understand more about the concepts. Our motion blur example, for example, takes about 2 minutes to render right now. Is that a long time compared to production level ray tracers? Absolutely. Is it too much time? Not for my purposes. That said, I think there's some utility in becoming a little bit more familiar with axis aligned bounding boxes, or AABBs, because they are used in other contexts as well. This is, after all, something that exists inside Bevy anyway. The axis aligned bounding boxes weren't that terrible to implement, but the bounding volume hierarchies were an interesting task. Not necessarily because they were interesting, but because the conversion from the C++ code to something that wasn't C++ felt kind of painful. I spent some time working on it, which you can see on the right here, but in the end, I decided it was more trouble than it was worth. In sum total, the concepts are basically merging ranges and iterating over them and then implementing hit for what is effectively a binary tree structure of bounding boxes, where the bounding boxes go from individual items that we can hit to wrapping 2 items and then wrapping 4 items and then wrapping 8 items and so on. This class of structures is referred to as efficiency structures or acceleration structures, and it is important if you're trying to write a production ray tracer or a real-time ray tracer. For us, though, because I found the C++ code a little bit tedious to convert, and honestly, the day I was doing this conversion specifically, I was quite tired for other reasons, I decided to skip this section after doing some of the implementation. That brings us to textures. Because we've got a whole bunch of files split out, I started off with a textures.rs file that implements a texture, one of which is solid color and one of which is checkered. This is an enum, again, because I find enums, in this case, to be the easiest to work with and the most extensible. We can always go later and make texture a trait or something else. But after the last section, the amount of back and forth is starting to wear me down. In section 4.1 and 4.2, we're supposed to implement solid colors and a checkered texture. And even though the example of it working shows in 4.2, it doesn't actually work for our materials until 4.4. All in all, getting the textures to actually work wasn't terribly hard. I just wish the code and explanations were given in an order that would have made the work a little bit easier to follow. Again, I went with the simple approach of making texture an enum, which I'm finding to be a good default choice as I go through this series. There are quite a few abstract classes, but turning all of these into traits and dealing with them would have been a lot rougher than just using a couple enums. Because we already have dvec3s representing colors for us, and we now have this texture solid color enum, I implemented from dvec3 for texture, so that we don't need to wrap everything in solid color every time we want to use a color. And our materials then start to use textures, which can be a color or a texture, instead of just a dvec3. With solid colors and checkered textures done, image mapping was easy to build on top of that infrastructure. Since we have texture as an enum, we add a new enum and drop in a small implementation for picking pixels. This is all made easier by the fact that Rust has the image RS crate, so we don't need to implement our own image reader like the series does here on the left. We can just open a path, decode the image, and use it. I find that implementing all of these little functions like this image loader really takes away a lot from the series as a whole, making a lot of the work here not actually understanding ray tracing, but divining which functions are necessary and what their names are in wider ecosystem. This also includes whether the specific implementations of those functions in the series translate well to the well-established conventions in other libraries. I chose to follow the Bevy convention of having an assets folder to store images and such in. I used the same image as the series, but ended up with a different rotation when actually viewing my earth texture on my sphere. With solid, checkered, and image textures done, it was time to move on to Perlin Noise. Unfortunately, this whole section is once again basically not something you're going to need if you have access to a noise generation library. In Rust, that's Noise RS, which provides not only Perlin noise, but a whole bunch of other noises and combinations of noises in various states. I ended up making it fairly easy on myself. I added Perlin Noise and Turbulence, which is another version of noise that they use in the series, into the texture enum. Then, of course, we've got our implementation. In this case, I ended up with Perlin Noise with a noise and a frequency, and then Turbulence. This allows you to configure and pass in any Perlin noise that you want, as evidenced by the Perlin Noise example, where we create Perlin Noise with some seed. In this case, we pass it into Turbulence and use that as our noise texture. Because it's a texture, remember, we can pass that into any of our materials as the albedo, or the color that we're using. That brings us to the first new shape introduced by the series that isn't a sphere: quads. Instead of implementing a box later, the book chooses to put a number of these quads together later to make a box-like object. Quads overall are pretty okay to implement. We've got the struct that defines them, a new function for initializing them, a utility function, as well as the hittable implementation. These are also the base for sources of light. Lights and emission produce a really nice effect. Basically, by multiplying the amount of emission, which is 0 for non-emissive materials, by the scatter color, which we're already rendering, we can render only the colors that the light is hitting. The implementation of light requires adding a new diffuse light that accepts a texture. It doesn't do anything when we scatter, but it does provide a color when we call emitted. Overall, introducing lights or light as the source of the rendered pixels on screen causes a lot of noise in our image, and this noise will stick with us through the end of the book. If a ray bounces off into nowhere and never hits any light, we'll see a black pixel instead of a rendered color. In any case, this effect is really fun and produced some of my favorite images from the series. In the next section, we translate and rotate some of these objects. It turns out that moving and rotating objects is less about moving and rotating objects and more about moving and rotating the rays that hit them. At this point, I feel like the APIs I've chosen for building out hittable things and shapes are all straining a little bit. Oh well, I did the best I could with the information I had. The APIs I've chosen to go with all work, so at least we haven't coded ourselves into an unevolvable whole, even if they're not particularly amazing to work with. The translate and rotate Y structs are added to the shape's enum, which at this point I feel like almost should be called hittable. While none of the other shapes have any modification to their object hit function, translate and rotate Y handle bootstrapping a new ray in a different position. For translate, we translate it, and for rotate, we rotate it. Then we forward it on to whatever object needs to actually be hit. This actually works surprisingly well. And the translation, rotation, and quads allow us to build what is commonly called the standard Cornell box scene. 2 boxes translated and rotated into position, surrounded by walls with a light on the ceiling. On then to fog and smoke. Fog and other volumetric materials were a topic I was really excited to get to. And to be honest, it helped me drive through some of the drier parts of this series, especially those sections that were just a slog conversion from C++ to Rust. Unfortunately, at this point, it really only took 2 paragraphs and a code block or 2 to implement the basic fog mechanisms. I guess I should be happy, and it looks amazing, but it also feels like there's a lot that could be done from here in the future. We implement a new shape called constant medium for these fogs. And basically what happens here is that rays shoot through a bounding shape, mostly passing through but sometimes scattering inside of it. Dense volumes, which we represent with an F64, are more prone to scattering, while less dense volume materials scatter less. There's another choice that the series makes where the normal, the front face, and I'm pretty sure the U and V coordinates are all arbitrary and commented as such, but there's no change in the structure that this returns or modifies to signify that, which again just feels a little weird to me. Overall, the fog is a very cool look, and it was overall pretty easy to implement. Of course, assuming that you already have the math. I've said a few times over the course of this video that performance hasn't really been a concern for us. I always knew a CPU-driven ray tracer was going to be slow, and that if I wanted performance, we'd look to the GPU. The final scene, however, really put that to the test. With the full settings they wanted to use, something like an 800 pixel by 800 pixel image with 10,000 samples per pixel and a max depth of 40 bounces, it was going to take my program potentially days to render, which was a little bit too slow for me. I knocked down the settings to render in an hour, but there's very obviously a lot, we'll just say slow, about the current implementation. I, again, didn't code this for speed and didn't even finish implementing the efficiency AABB and BVH structures. So that's to be expected. Honestly, I don't know that I could have coded this to be a faster program at this point, given that during the series, I didn't know where the series was going before I started writing code. At this point, I'm happy with where the ray tracer is, and I'm ready to move on to maybe a WGPU-based implementation. I skimmed the content of book 3, and I don't think it will be of much use to me until I start building more ray tracers and start running into more real problems with them. I've purchased a different book that some people suggested arriving soon, or actually already here now, the Ray Tracer Challenge. I might do that. I'm really interested in global illumination right now though, so I think I'll get into some of that. There's a paper here on the right that caught my interest, Radiance Cascades, a novel approach to calculating global illumination, and some really interesting work in the Bevy ecosystem on the left here. This repo is called Bevy Magic Light 2D. If you made it this far, thanks for watching, and if you go through the ray tracing series, perhaps in Rust, perhaps not, please leave a comment and let me see some of the images that you create. I'd love to see how you get on with it and compare. Have a great rest of your day, and I'll see you in the next one.